Thank you for the introduction. Hello, everyone. First of all, I would like to thank both the organizing committee and the Clay Conference Committee for giving me the opportunity to present my work here today. This work does not properly focus on the opalinous clay, but rather on the French Calavo-Oxfordian claystone, and investigates how 3D hydromechanical modeling can support the design of a backfill experiment in this formation. Before starting, I would also like to give credit to my colleague at the university, as well as to Andra's collaborators for their valuable contribution to this work. So let's start with a short contextualization. And the general context of this presentation is the closure phase of the CGO repository, which is characterized on the one hand by the local implementation of sealing systems, and on the other hand by the global backfilling of the storage galleries. And this process of global backfilling, it is mainly dedicated to limiting the extension of the EDZ after the collapse of the lining system, and also providing a low resistance to gas flow. And so in order to demonstrate the technical feasibility of building a backfill solution on a repository scale, the ANDRA has developed a research program, and part of this program takes place in the underground research laboratory already introduced in Gilles Armand's presentation, where a full backfill solution will be implemented and monitored. And based on the given specifications, it is possible to describe all the components of this experiment. So there is first the backfill itself, which has a cylindrical shape and a length of 10 meters. 7 geotextile membranes are disposed on the outer face of the backfill in order to artificially saturate this system. This system is surrounded by the concrete support structure and takes place in the Calavo-Oxfordian claystone with an excavation damage zone. All these components, they have their own hydromechanical properties, and especially we are focusing on two types of backfill materials: a full section of sand-dominated backfill material on the one hand, and a two-layer mixture composed or including also a clay-dominated backfill composition on the other end. After the placement of the backfill, there are several phases, and especially the hydration phase, with the aim of identifying the best hydration scenario, followed by the test performance phase, which aims at assessing the hydraulic performance of the system. And so, from this specification, the main objective of the work was to support the overall design of this backfill experiment through the use of 3D modeling simulations. So let's now move on to see how this experimental configuration can be translated into a numerical model. And first of all, the numerical tool that is used for these simulations is the nonlinear finite element code Lagamin, originally developed at the University of Liège. And the Lagamin code compiles specifically constitutive laws with finite elements in order to investigate a wide range of civil engineering applications, including the deep geological disposal that is the topic of the presentation. And so using this tool, it is possible to convert the experimental configuration to be studied into a 3D hydromechanical mesh, taking the effect of gravity into account, and also considering only half of the mesh due to the symmetry effect. And regarding the boundary condition to be applied, all the displacements are supposed to be constrained on the outer periphery of the domain. And for the hydraulic boundary conditions, all the borders are supposed to be impervious, except at the outer part of the downstream part of the domain, where the EDZ serves as an outlet. The different phases are simulated by progressively updating the boundary conditions, and during the hydration phase, all the geotextile membranes are activated as water injector with a maximum injected flux of 5 millimeters per minute. And then during the performance test stage, there is a specific condition that is imposed at the upstream membrane S1 until a steady state gradient is established through the backfill and detected at the downstream membrane S7. And for this phase, two main types of conditions are studied. a pressure controlled condition on the one, pressure condition, control condition on the one end, and a flux control condition on the other end. Then the hydromechanical behavior of the system has to be described, and it is done by considering that each of its components is treated as a porous medium. That is how it is done in the code. And this porous medium includes three main phases: the solid phase, liquid phase, and the gas phase. And each of these phases include different species, so mainly mineral species and different types of water and gas species. And from this formulation, this gives rise to different balance equations: the balance of momentum, balance of water, and balance of gas. And these equations, they include three main unknowns: the displacements and the water and gas pressures, and also dependent variables such as the degree of saturation, the fluxes, or the stress tensor, which can be expressed in the form of a constitutive equation. And finally, these constitutive equations, they are used to link the dependent variable to the main unknowns of the system in order to fully describe the behavior of the porous medium. Then regarding the material parameters, each component of the system is basically assumed to have a linear elastic behavior, as we are mainly interested in free flows. From a hydraulic point of view, they have all an intrinsic permeability that is assigned with 1 order of magnitude difference for the two types of backfill material that are examined. And these materials, they are also assigned a retention curve of Van Gunnectum type, as well as water and gas permeability curves in order to fully describe the hydraulic behavior of the system. So that's it for the description of the model, and let's now continue with the simulation of the hydration phase, focusing more specifically on the optimization of the system design. And to do so, we only consider the backfill and the geotextile membranes, and the rest of the system is neglected for the moment. And for this reference reduced geometry, the progressive resaturation of the backfill is achieved through the simultaneous activation of the different membranes, leading to a fully saturated state at the end of the simulation. So if we take a closer look at different sections of the backfill, we can see that the saturation initiates from the entire section at the upstream side of the domain, while it starts from the periphery in the other section of the backfill, finally establishing according to gravity and leading to a full resaturation after more or less 260 days. Then the effect of the number of injectors on the resaturation process can be investigated with respect to the reference reduced geometry on the right. And in this case, we can see that the progressive resaturation of the backfill occurs quicker or faster, which was more or less expected. And if we take a closer look at different sections of the backfill again, we can see that basically we have more or less the same trend in the resaturation process, except that increasing the number of injectors reduces the resaturation time to more or less 150 days. And finally, the effect of the activation strategy can be investigated with respect to the reference reduced geometry. And for this case, we will switch from a simultaneous injection of the injectors to a stage-wise injection of the injectors. And for this updated configuration, we can see here that the progressive resaturation of the backfill occurs from the upstream side to the downstream side through the propagation of a water front, leading to a full resaturation of the backfill. So if we take a closer look at specific sections, we can see here basically that we still have more or less the same trend in the resaturation process, except that the stage-wise activation of the injectors reduces the resaturation times and also leads to a more uniform resaturation of the backfill. So as preliminary conclusions regarding the optimization of the design of the system, we have demonstrated that the artificial hydration of the backfill through the use of geotextile membranes allows to mimic the progressive resaturation of the system and also to reach a fully saturated state of the system. So this artificial resaturation is required. But the duration to achieve this fully saturated state of the backfill depends not only on the number of injectors, but also on the activation strategy, which can leave an unsaturated zone inside the backfill and which could be problematic. And also, in addition to gravity, there are other parameters governing the resaturation of the backfill, and especially the parameters of this backfill, so mainly the permeability or also the porosity. And that's the reason why we will now switch to the simulation of the hydration phase with a focus on the optimization of the composition of the backfill. For this simulation, again, we consider only the backfill and the geotextile membranes. And initially, we consider a section of the backfill that is clay-dominated. So it means that there is 30% of sand and 70% of crushed claystone. And for this configuration, the progressive resaturation of the backfill initiates quite quickly at the upstream side, but then we can see that it struggles to penetrate deeper inside the core of the backfill due to the very low permeability of these types of backfill, so the clay-dominated composition of the backfill. And so if we take a look at the different sections of the system, we can see that we have very fast resaturation of the section close to the upstream injectors, but we have a significant resaturation delay for the other sections of the backfill, which is problematic. And so the idea was to switch to another configuration with a sand-dominated backfill composition on top, which is more permeable, and a clay-dominated backfill composition at the bottom, which is less permeable. And in this case, the progressive resaturation of the backfill appears to rapidly resaturate the sand-dominated part of the backfill, while it takes much more time to resaturate the clay-dominated part at the bottom of the system. But in the end, we can reach a full saturation of the system. It takes the 500 days of simulation. So analyzing more in detail the different sections, we can see more or less a similar trend in the resaturation process with a rapid resaturation of the section close to the upstream injector. But still we have an important resaturation delay between the upper part of the backfill that is more permeable and the lower part of the backfill that is less permeable. And so the last configuration to investigate is to consider only the sand-dominated So we consider only the sand-dominated backfill material for the whole section. And in this case, the progressive resaturation of the backfill appears to propagate from the upstream side to the downstream side through the propagation of a waterfront again, leaving a more uniform resaturated state of the backfill. So basically, if we take a closer look at the different sections, we can see here that the sand-dominated backfill composition leads to faster and also more uniform resaturation of the backfill. So it's beneficial for this experiment. And so as preliminary conclusions regarding the optimization of the backfill composition, we have demonstrated that the backfill parameters and especially the permeability play a key role in the resaturation process. We have seen also that the clay-dominated backfill composition that is less permeable leads to a less effective resaturation process, while the sand-dominated composition that is more permeable leads to a more effective resaturation process through the propagation of a waterfront. And yet, to get a complete understanding of the problem, we have to investigate the full geometry, including also the support structure and the Kelovox for the claystone plus the EDZ. So that's the objective of this phase. So we will simulate the hydration phase, considering the full geometry, the selected backfill composition, so it's the sand-dominated backfill composition, as well as the selected system design. And in this case, the results in terms of saturation on the left and water pressure on the right, gives an overview on how the system progressively resaturates through the propagation of a waterfront, which is initiated by the stage-wise activation of the injectors at the top of the domain. So we can see that we reach full saturation for the 500 days of simulation. And basically, if we look at the different sections of the backfill, we can see that the conclusions are more or less identical to those of the reduced reference geometry. So the resaturation is fast and more uniform. And for this final configuration, we can also take a look at the fluxes in the injection lines, where we can see that we have initially the progressive activation of the different injectors, and then we have a slight decrease as the saturation of the backfill progresses, finally leading to residual values of fluxes that are in equilibrium with the fluxes that is computed at the EDZ, through the EDZ. And in parallel, we can also compute the injected volumes through the different injectors, as well as the volume that is extracted through the EDZ. And this gives an idea or an estimate of the total amount of water that has to be injected in the system to reach the fully saturated state, which is estimated for these simulations around 6,000 liters. Finally, for this final configuration, we have also investigated, or we have also performed a sensitivity analysis on the permeability of the backfill, since it is the governing parameter of the simulations. And if we take a look at the different sections of the system, we can see that the resaturation time increases non-linearly from more or less 150 days to more than 1,000 days, as the permeability decreases of 2 orders of magnitude. And from these results, it is possible to build a map of the resaturation time as a function of the permeability. And on this map, it is possible to compare the reference or the final configuration with the reference reduced configuration, so they are close to each other here, and also with the 2-layer backfill configuration. So this kind of map gives a valuable tool for the optimization of this kind of experiment. So that's it for the hydration phase. Let's briefly investigate the performance test phase before concluding. And considering first a pressure-controlled condition, applying a pressure gradient of 5 MPa over 5 days, during a period of 5 days, we can see that this condition is directly translated into an input flux in the upstream membrane in blue that is progressively equilibrated by the output flux through the downstream membrane in red, plus residual flux through the EDZ here in black. And this analysis is corroborated by the computation of the volumes here at the bottom, where we have the volume in the injected membrane in blue, in the detected membrane in red, and in the EDZ in black. In terms of pressure for the performance test, we can see that the system stabilizes at a pressure of 5 MPa, close to the upstream section, and at lower levels of pressure for the other sections of the backfill due to the beneficial drainage effect of the S7 membrane, so the downstream membrane. So this leaves quite acceptable levels of pressure. Switching now to the flux control condition, applying a harmonic condition, so a harmonic flux of 20 milliliter over a period of 10 days. We can see that this condition again is translated into it's translated into an oscillating flux, input flux in blue in the upstream injector. That is, there is a slight delay, but it's then equilibrated by the output flux in red through the downstream membrane, plus a residual flux here in black computed through the EDZ. Again, the computation of the volumes can corroborate these results. And if we take a look at the pressures, we can see here that the system stabilizes around 1 MPa maximum, which is quite acceptable. and at lower levels of pressure deeper in the system, again due to the fact that the S7 membrane here can be used as a drainage function. And finally, we can investigate a case where this S7 membrane does not work as a drainage function. And in this case, we can see that, oh, a bit too fast. We can see that the input flux through the upstream membrane, in dotted blue, is here progressively equilibrated by an oscillating flux through the DZ, but the steady state is not yet reached at the end of the 100 days simulation. And what is interesting is to look at the pressure, because in this case we can see that there is a continuously increasing level of pressure in the overall system up to 10 MPa, but it will keep increasing for a couple of days, which is in this case less admissible for the experiment. And this emphasizes actually the role of this S7 membrane that has to be used in drainage. So now this is time for the conclusions. And if we get back to the title and the question of this title, we have seen, which was that we have to support the design of the backfill experiment in the Calov-Oxfordian claystone. So in this presentation, we have developed a 3D hydromechanical model that is able to reproduce the geometry, the full-scale geometry of this experiment. This model is also able to mimic the artificial hydration of the system through the activation of the different membranes, leading to a fully saturated state of the backfill. And finally, this model was able to simulate the hydraulic performance tests. And so using this model, we have demonstrated that the stage-wise activation of the injectors is preferable for the hydration process. We have also shown that the sand-dominated backfill composition is also preferable to have an optimal resaturation process. We have demonstrated that the resaturation time, so that was computed around 250 days for the reference case, as well as the injected volumes, around 6,000 liters, are strongly dependent on the backfill parameters, so basically the permeability, but also the porosity. And finally, we have shown that the S7 membrane that acts as an outlet during the performance test is very important to avoid inadmissible levels of pressure during this phase of the test. And just a last word to say that this work is not, I would say, finished. It's still possible to improve. And so we plan to refine the backfill behavior by considering another kind of model, and for instance, the Barcelona basic model, for those who know it. And we plan also to monitor the deformation in the system. And so that's it for the presentation. I would like to thank you all for your attention.